There we go. So today we're continuing on our journey of rigid body kinematics. Wanted to look at three problems. We looked at one on last week, and today we're going to look at two problems and get into some more theory. All right, and then today I will also post the next homework 7. So you guys should be ready and prep for that. So with that, let's get a move on. So this is problem number 4 from your problem statement, whereby you have the rod BE, which is rotating about the point E, and it's going counterclockwise, and you're asked to find the angular velocity of the rod AD, which it's linked to with point B, and you know the point D moves on a collar, and it can only move vertically up and down. And then you're also asked to find the velocity of the point A. So you can do this problem totally just using your relative velocity equations for rigid body motion, right? And this is the way that you should think about doing this. You can look at link EB, find out what VB is, and then just look at VD, right? Because for VD, you know that VD is going to be in moving in an up and down direction. So that only gives you one unknown. So with that unknown and with omega AD as the unknown, you can just look at VB with respect to VD and find out what your velocity for D is, because you know you can describe the motion of B due to the rotation of EB, right? And then using that, you'll have the velocity of point A, where you'll have two unknowns, because both the direction of the Vx component and Vy component is going to be unknown, and then you can solve that knowing what omega AD is. So that's just the traditional way of solving the problem, the exact same way which we did it last time. We can do that, but there is a slightly quicker method to solve this problem, looking at the instantaneous center of rotation. So that's what we're going to do. We're going to look at this alternative approach to solve this problem. So before we get into it, the first thing to do, what's the first thing to do while solving our problems?
Free body diagram.
Nope, we're not looking at free body diagram here, because we're not looking at forces, but close, coordinate system, right? So y, x, and our z is coming out of the page, right? So what we can do now is that we can look at link BE to completely describe the motion of the point B, right? So looking at link EB, I can say that the velocity of the point B at this particular instant is equal to the velocity of the point E plus omega EB, which is given to me in the problem, right? It's saying it's 4 radians per second counterclockwise, crossed with R of B relative to E, like that, right? So in this expression, what is velocity of point E? Zero. It's fixed, right? Doesn't move. All right. Then from the problem statement, I'm told that omega EB is 4 radians per second counterclockwise, right? So counterclockwise being positive, it's going to be 4 k hat radians per second. And I'm not going to use Mathematica for this problem, just for the interest of time. So remembering for the cross product, I crossed with j is positive k. So I cross with j is k, k cross with I is j cross with k is I. All right. So this is the positive motion for how the positive movement for how the cross product works. All right. So next we have to find out what R of B relative to E is, right? So R of B relative to E, you're just going 192 millimeters in the negative y direction, right? So this is just going to be, let's just convert it into meters, minus 0.192 j hat meters, like that. So now we can fully describe the velocity of the point B. So velocity of B is just equal to 4 k hat crossed with minus 0.192 j hat, right? And this is going to be radians per second. This is in meters, so I'm going to end up with meters per second, right? So 4 times 0.192 is how much, guys? How much do you guys get? Minus. Anyone? No one?
Negative 0.768.
That's right. All right, negative 0.768. And k crossed with j is what? K crossed with j?
I.
Nope. Negative I, right? So j cross with k is positive I, k cross with j is negative I, all right? Meters per second. So you end up with 0.768 I hat meters per second. All right. So now what we can do is when we're looking at this link AD, the other way to solve the problem, which I'm just quickly going to write out the expressions for you guys, is you can do VD is equal to VB crossed with omega, oh, no, sorry, wrong, plus omega AD crossed with R of B relative to D, right? This is how you would originally solve the problem. And this equation, you need two unknowns, right? So here, that's going to be one unknown. And here, you can say this is going to be one unknown because we know that VD can move horizontally. You can just say that this is VD J hat, all right? This is how you would solve the problem. So you'd get omega AD, you'd get VD, and you'd solve your problem. And then you can just do the same thing for VA, all right? That'll be two more expressions. But we're going to look at the instantaneous center of location. All right. So in order to do that, by the way, before I do that, are you guys clear with this method of how to do the problem? Right. This equation is going to give you two unknowns, VD and omega AD. You solve for those, and then you just like go back to your expression for A, whereby you'll get VA is equal to, you could use either B or D, doesn't matter. So B plus omega AD crossed with R of A relative to B, like that, right? Or R of B relative to A, sorry. Actually, no, it's I wrote this equation wrong. It's R of D relative to B, and then R of A relative to B over there. All right, and then here, this one has two unknowns, all right? But everything here is known, so you're good to go. So two equations for two unknowns here, two equations for two unknowns here, because here you don't know the x and the y component. All right, so this is how. Yeah. Go
I
ahead.
have a question.
Yeah.
So angular velocity is in radians per second,
Yes.
right? And R is going to be in meters.
Correct.
So angular rad per second crossed with meters is meters per second.
That's right. Radians is unitless dimensions for angles.
Okay.
That's absolutely right. Yeah. Okay, but now we are going to do this using the instantaneous center of rotation. So in order to do that, so alternatively, use instantaneous center of rotation. And here, the beautiful thing about this is you don't need to make any assumptions about things because you already do that when you find out where this is going to be. So we do is, let me get out drawing skills. So you've got the point E, right? That's going down like that onto the point B. That, all right, I think this is good enough for now. So here, at this particular instant shown, we know because EB is like that, VB, we found out, we also know this intuitively, but we know that it's in the I hat direction, right? And then VD, we know is the caller, right? So that's going to be moving in either the downward or the upward direction. The answer will tell us what the direction is. You can just assume it to be one way or the other. But I'm just making this assumption based on what this motion is and what my intuition is telling me. But you don't need to do that. All right. Then to find out the instantaneous center of rotation, what we do is you draw the perpendicular from VB, you draw the perpendicular from D. Boom, you get the instantaneous center of rotation. All right, and in the problem statement, we're told that this angle is equal to 30 degrees.
And so C was referred to as the instantaneous center of rotation.
In the instantaneous center. So you can describe the motion of any rigid body at a particular instant from a point whereby all the velocities intersect. Right? That's what we derived last time. So now you can even do it for VA, whereby you draw a line there, then you know that your velocity of that point is going to be perpendicular to that line, right? So you've got point B, point D, point A over here. All right, so now to find out AD, what I can do is to find not AD, sorry, omega AD, what I can do is I can look at point B with respect to C, right? And I get my expression that VB. And if you're not sure of the instantaneous center of rotation expression, you can just use your general equation and then take it from there, right? So you can say that VB is equal to velocity of the point C plus omega AD crossed with R of B relative to C. All right, but we know from a fact that the instantaneous center of rotation is going to be what? What's the velocity going to be at the instantaneous center of rotation?
0.
0, right? That's why it's the instantaneous center of rotation, right? So here I have my unknown omega AD is equal to omega AD k hat, and that's what I'm trying to find. So here I get one expression for one unknown, and I solve for omega AD. I just need to find out what R of B relative to C is, right? So R of B relative to C, so going back to the geometry, told that this is 360, and then this length here is 240 millimeters, right? So for R of B relative to C, I'm going in the positive j hat direction, right? So my vector is positive j hat. And what's the magnitude going to be for BC? Triangles. Come on.
Sine of 30.
Sine of 30 times what? 360, right? So it's going to be converted into meters though. So you get 0.36 sine of 30. And this is in meters, right? So it's, I believe sine of 30 is 1/2, right? Yeah, it is. So this comes out to be equal to 0.18 j hat, like that. All right, so plugging everything into this expression, all right, before I move on, everyone good with this page? Moving a little quickly today. Good? Okay. Come on. All right. So next, we plug in everything. What we found so far for VB, we found that was 0.768 I hat meters per second, and that is equal to omega AD, the unknown that I'm trying to find, k hat crossed with R of B relative to C, which we just found was 0.18 j hat. And this whole thing is going to be in meters per second. So this is equal to 0.18 omega AD, right? And k crossed with j is equal to minus I hat again, right? So I get minus I hat meters per second here. So from this expression, I see that omega AD is equal to minus 0.768 divided by 0.18 radians per second. That turns out to be how much, guys?
.266 or negative.
Yeah, so minus 4.27 k hat radians per second. So what that means is that this link AD is moving clockwise. All right. So that's your first problem that you're looking for. All right. Well, this is for minus 4 that. So omega AD is equal to minus 4.27 k hat radians per second. All right. Next part. So this was part A. So for part B, what you're trying to do is you're trying to look at the velocity of the point D, right? And VD, you don't even need to worry about the direction here, right? Because you've already accounted for this being vertical when you drew this perpendicular line, right? So you can just straight off write the vector expression saying that that's equal to omega. All right, if we do it completely with respect to the instantaneous center of rotation, it's VC plus omega AD crossed with R of D relative to C, right? Instantaneous center of rotation, we know that that guy is equal to 0. All right. So now we know what omega AD is, right? So omega AD is minus 4.27 k hat, and we're crossing that with R of D relative to C. So R of D relative to C is going to be in the positive I hat direction for this instant, right? And then what's the magnitude going to be equal to? What's the length DC?
Cosine 30.
That's right. So 0.36 cosine of 30 degrees, right? And this is in meters. So this ends up being square root of 3 over 2, 0.36. Can you guys quickly check this? I got 0.312 I hat meters. 0.312.
Yeah. So wait, for A, is that what we were trying to do for A? Was find that?
No, this is for D. Well, right
No,
now,
I know, but we solved for part A. Was that really part A of this question?
yeah, part A was the angular velocity of AD,
okay.
and that's what we
Okay.
found. What's up, Mr. Rushford? Woke up on the wrong side of the bed today?
Yeah, always on Tuesdays. Yeah.
Tuesday is your middle of the week, right? Yeah. All right. So that minus 4.27 times, so k cross I is going to be minus j, right? No, k cross I is going to be plus j. So you get j hat, and then you get minus 4.27 times that. So that, can guys confirm this? I got minus 1.33. By the way, did someone confirm? Is it 0.32 here?
Yes.
It was 0.312. Yeah.
Okay, so then I think this should be correct as well. All right. Wow. Quickly solving problems. That's the second part solved. The last part is where you might say, all right, Ashish, now you might think that, all right, this is where the instantaneous center of rotation might not make sense because you need to do a little bit of extra work. So now you can say that VA is equal to, and again, always referring to this diagram over here, right? So V of A, you know what? Let me do it this way. Come on, go down, go down. Oh, PowerPoint. All right, there you go. Okay, so here we say that V of A is equal to V of C plus, oops, not plus, plus omega AD crossed with R of A relative to C. Instantaneous center of rotation, V of C equals to 0. So here, the trick is that we really just have to find this guy over there, right? So R of A relative to C. So R of A relative to C. So now what I do is, and this is where the solutions from your book. So going forward, no more solutions from the book for your problem sets, only for your homeworks. And then also, well, I'll be posting the solutions for today's problem set from the book, but going forward, we're only going to look at the problems that we look at in class, and we will only look at the solutions that we do in class, all right? Because I don't like the book anymore. So here, if you draw a horizontal line out from A, right, you call that point F. If you look at your solutions, they just say that E is F, which is not true. All right. So please consider the point F like that if you want to be complete about it. All right. So now in my coordinate system, R of A relative to C, right? I'm going CF in the positive y direction. So it's going to be equal to CF J hat. And then I'm going AF in the negative I hat direction. Right? So it's going to be minus AF I hat. How are you guys with position vectors and things like that? Is this good? Does this make sense? R of A relative to C is going to equal CF J hat times AF minus I hat.
Sorry, I think I lost
I
you.
enjoyed your expressions, Mr. Simpson. It was like, what the hell is going on here? No, it's R of A relative to C, which is this line here, right? I'm going to go CF in the positive J direction, and then I'm going to go FA in the negative X direction. That's exactly what I have over here.
Okay, I got you.
All right, you guys need to be able to do this. Like, did you go watch the Khan Academy videos?
I will today.
All right, okay. So here, next, then the trick becomes AF is going to be easy, right? So AF, we can find out. So this is 30 degrees. This is going to be 30 degrees. So AF, we can find out from here. So that's the easy part. CF is going to equal the length CB plus the length BF. So you got to look at two triangles, right? Shut up, triangle boy. Sorry. Yeah, I'll always be that guy. So it's going to be CB plus BF. All right. So and also make it a little more clearer. This is the point B. All right. So CB is what?
0.36 sine 30.
That's right. 0.360. Oops. Sine 30. And then what is BF besides best friend? Which I need.
0.24 sine 30.
Exactly. So 0.24 sine 30 degrees. Right? That's equal to, sine 30 is half. So you get 0.36, 0.24, that's 0.6. So you get 0.300 meters. Quick maths. All right. AF is equal to what?
.24 cos 30.
Exactly. 0.24 cosine 30. That's equal to 0.207. 85 meters. Sorry. All right. Let's go. We'll just write that. All right. Then you see that R of A relative to C is equal to, we said minus AF I hat, right? So minus 0.20785 I hat plus CF J hat. So plus 0.300 J hat meters, like that. All right, plug and chug, plug and chug. So V of A is just equal to omega AD crossed with R of A relative to C, right? So that's just equal to, what was omega AD? Minus 4.27, right? Yeah, minus 4.27 k hat crossed with R of A relative to C, which is this guy, so minus 0.20785 I hat plus 0.300 j hat, like that. So this is in meters, radians per second. So you end up with meters per second. All right. I'll let you guys do the math because now it's pretty straightforward. Blah, 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 k cross I. K cross I is equal to positive j. K cross j is negative I. You know, do that. The final answer that I got was 1.281 I hat plus 0.89 j hat. That's it. All right.
Why did you choose to do CB plus BF and not just, you know, AD sine 30?
You could have. You totally could have. You totally could have done that. I just did it because that's literally what it was on the diagram. But
I
you know,
see. Right.
you're absolutely right. You could have just drawn it out like that, and then found out that length, which is the same as that length. Same thing, same diff.
And do you want them in those the answer in that kind of?
You give me a frame of reference. If you give me a coordinate system and give me an answer in terms of that coordinate system, the unit vector is there. You will always get full credit.
Okay.
You don't need to do the magnitude and angle like the book does, right? Because those are also magnitude and direction, two unknowns, I hat and j hat, two unknowns, the same thing. Right, let me know when we're good to move on to the next question. Or if you have questions with this question. How's everyone doing?
Catching up, getting there.
Let me know if I'm moving too fast. The last year's cohort in dynamics changed my name to Lamborghini.
I don't know. I feel like you go fast, but at the same time, I feel like I need to go faster. You know, I'm just.
Hey, it
like,
is dynamics,
really
right? So you might as well. Okay. No, we need to go fast because we've got a lot of stuff to cover in the next 3 weeks. All right, good? Easy peasy? All right, next question. Moving on. So next question is basically the same thing as the first question, but we're looking at accelerations. So you have this link AB and then this link DB, right? And you're told, and this is going to be problem number 5, I believe, in your problem set. And you're told that the crank AB rotates about point A at a constant angular velocity, 900 RPM clockwise, right? And you're asked to find the acceleration of the piston P when theta is equal to 60 degrees. So that's instant when theta is equal to 60 degrees. All right, first things first, let's just find out what omega AB is by converting the 900 RPM, right? So you have omega AB, and remember, you know, we're always going to be using Y, X, and counterclockwise Z hat positive, right? So this is going to be minus, because it's clockwise, it's minus 900 when you're converting RPM into radians per second, right? Revolutions per minute, 1 revolution is equal to 2 pi radians. 1 minute is equal to 60 seconds. Right, so this turns out to be equal to minus 94.24 radians. Can you guys confirm this one real quick? So I say that my omega AB as a vector is minus 94.24 k hat radians per second.
94.24. Got it.
Awesome. All right. So now let's look at accelerations, right? So when I'm looking at the link dB, right, I can say that the acceleration of point D is equal to the acceleration of point B plus alpha dB crossed with R of D relative to B plus omega dB crossed with omega dB crossed with R of D relative to B. And how many equations is this? One vector expression?
Sorry, what was that?
How many expressions is this vector expression? How many equations do you get from here? Guys, making it
You
easy.
get 2 because it's in 2D.
Exactly. Whenever you're looking at plane rigid body motion, your vector equations will always give you, one vector equation will always give you two expressions, one in I hat, one in J hat. All right, that's just how vectors work. It's magic. All right, so here, all right, what we can do is, we don't know what omega dB is, right? Geometry of the problem, we can always find out what RdB is, so RdB is known. We don't know what alpha dB is either. And although we're told that AB moves with a constant angular velocity, that means that alpha AB is going to be 0. But that does not mean that alpha dB is, we can't assume that alpha dB is going to be 0 from the get-go. All right? This AB having a constant angular velocity does not mean that dB is going to have a constant angular velocity. You cannot make that assumption. All right? Any questions with that one? All right, so here, this one is an unknown as well. All right, here, acceleration of B is a tentative unknown because we can look at B with respect to AB as well, right? So that's, we're going to get two more expressions from there, right? So I'm going to leave that. And AD is also an unknown. So clearly, too many unknowns for just two expressions, but we can make our life easy. What can I say about AD?
It's linear, so it can only go in the I direction.
Exactly. Because it's constrained to move only in the vertical, I know that the acceleration component, so only one unknown, not two. All right, and alpha dB, I can just say, let's just say that that's alpha dB k hat. All right, so in essence, in this expression on top, I've got three unknowns, right? Well, four unknowns because AB has two components. All right, now what we do is, so we need more equations, right? So now you got to look at link AB, right? So AB is going to equal the acceleration of point A plus alpha AB crossed with R of B relative to A plus omega AB crossed with omega AB crossed with R of B relative to A. All right, let's look at this equation now. Right here, right, I've got R of B relative to A, geometry, always easy to find. Omega AB is given to me in the problem. What can I say about alpha AB?
It's 0.
It's 0, right? Because AB crank is moving at a constant angular velocity, so it's not going to have any angular acceleration. So this whole term is 0. What can I say about the acceleration of point A?
So 0?
0, right? Fixed point. Easy peasy.
So earlier when you said that just because it has a constant velocity doesn't mean we can assume the system has zero acceleration. Only that component has zero acceleration, correct?
Exactly.
Okay.
All right, so let's do some counting. I've got 4 expressions, and I've got one omega dB, another one alpha dB, another one AD, and I've got 2 unknowns here for AB, right? That gives me 2 plus 1, 3 plus 1, 4 plus 1, 5. I'm still an equation short. Ideas, ideas, ideas. Where do I get the additional equation from? By the way, are you guys clear on why we're short of equations, right? Omega dB is unknown, right? That's going to be one unknown, because you can say that omega dB is just equal to omega dB k hat, right? So that's one unknown. Alpha dB is another unknown, so that's 2. AD is another unknown, that's 3. AB, 2 unknowns, right? Because it's going to have components both in the x and the y, so that's 5. So you have 5 unknowns, but you only have 4 equations over here. Where do you do? What do you do?
Would you use a trigonomic identity?
How would that help you out?
I don't know. I'm asking you.
Oh. Great. Flipped classroom. No, you do have to use a trigonomic identity, but before you do that, you've got to do something else. So the big unknown here that you have no idea where to find it is this, what you got to recognize is this omega dB term here. So how can you go about figuring that guy out? Read the problem statement again.
Well, WAB.
Mhm.
So you could use that some
So
way.
right now, we've only been looking at accelerations, right? So what can I do to get more equations?
Velocity.
Exactly. You can look at the velocities to get your additional equations. All right, because I can say that for link BD, I can say that the velocity of point D, right, is equal to the velocity of point B. And this is the problem we solved last week, right? So velocity of point D is equal to the velocity of point B plus omega dB crossed with R of B, R of D relative to B, right? And then for link AB, you can say that V of B is equal to V of A plus omega AB crossed with R of B relative to A. And what's V of A equal to? Zero, right? It's 0 because A doesn't move. Oops. Right? This term here is equal to 0. So let's define the unknowns over here. What can I say about VD?
It's only in the I hat direction.
It's only in the I hat direction. So VD, G hat like that. right? Plus, you have the unknown of omega dB, which we've already defined. So omega dB in the k hat direction. Now, guys, you have 8 unknowns and 8 expressions. Like, Ashish, we don't believe you. All right, let's count. From here, we had 5 unknowns. Here, you effectively only introduced 3 unknowns. 1 for VD and 2 for VB. So you have left with 8 expressions for 8 unknowns.
Do you ever have like a general rule of thumb of like going too far down the rabbit hole? Because I was like hesitant because of like introducing more unknowns, and I feel like it would get lost.
That is how I think about it. It does make sense to me. The other way you can think about it is intuitively from these 2 acceleration expressions here, the only thing that's here that you cannot get from these 2 expressions over here that you can maybe get from looking at velocities is the angular velocity. And if there is an angular velocity term which is extra and is unknown from your acceleration terms, you will always have to look at the velocities to find that out. And that's it. That's your rule of thumb right there.
Okay.
You keep building, right? Earlier we were looking at just velocities, but now when you look at accelerations, you will also have to look at velocities to look at accelerations. All right, now it's just a matter of, all right, you know what? Let's just recap. We have one, two, nope, not 2, like that. 2, 3, and 4, right? So you have 2, 4, acceleration of D equals AD. You know what? I'm not going to write. It is or you could cut these down too, guys. You can just, you can plug in this expression into here and plug in this expression into here, and then you're just left with you've taken out 2 expressions, but you've also removed 4 unknowns, right? So then you're left with 4 equations for 4 unknowns. That's just algebra. All right. So before we wrap things up, what is the one thing we haven't done?
Found the answer.
Right. No. In order to find the answer, there's one thing we haven't done. All right. These numbers that I'm writing here are just the unknowns. So I've got 1 unknown for AD, 2 unknown. The second one is for ADB. The third one is for omega dB. The fourth and the fifth one are for AB, which is not really an unknown because you just substituted it in, but you can do that in Mathematica. And then you have the 6th unknown, which is VD, and then you have the 2 unknowns for VB, which is 7 and 8. All right. Okay. What's the one thing that we need to do in order to solve the problem? What have we not found out in our expressions, guys, that we can?
Omega dB.
That's an unknown. No, we haven't found out what our position vectors are, right? So that's all that we need to do to set the problem up. All right. So we need to find out R of B relative to A and R of D relative to B. Those are the only two things we need to find out. All right, so let's do by the way, guys, does this all make sense?
Yeah, I feel like it's kind of long, but I think I'm like tracking and understanding where like how we're progressing. It's just like a lot to take in, I think.
Good. Okay. On paper, this is more difficult than what we've been doing so far, but because we're being so thorough with it, you guys will see that this is actually easier. All right, so you have a B, right? And that we're told makes an angle of 60 degrees. So if this angle here is 60 degrees, this angle here is going to be 30 degrees, right? So and the length of AB is what? Is 50 millimeters. So this is 50 millimeters, right? So what you need to do is that R of B relative to A is you're going to go, let's say that that's point C. So you're going to go AC in the I hat direction, and then you're going to go CB in the J hat direction. Right, so AC is going to be quick, 0.05 times cosine 30. I hat plus 0.05 times sine 30. Got 0.0433 hat plus 0.025 J hat. I think this is right. You guys can double check. All right, and then for your R of D relative to B, this one's a little more complicated. We have to use trigonometry. I believe that was Mr. Stroud who told us that. That was a beautiful suggestion. So we look at AB, then you've got DB, right? So you draw that perpendicular down. So you got A, B, and D. And you're told that this angle is equal to 60 degrees. This length is 0.05 meters. And this is dB is 150 millimeters given the problem. So that's 0.15 like that, right? So in order to find R of D relative to B, I really need to find this angle. Let's call that equal to beta. Right, in order to do that, how do we do that? Mr. Stroud, are you there?
Yes.
So how do we do this? Trigonometry, magic.
Well, I was thinking law of cosines, but
Almost there. Law of sines is the easiest way to do it, right? Because you can say sine of beta over 0.05 is equal to sine of 60 divided by 0.15, right? Angle, sine of the angle over the opposite side. To do that, beta is equal to 16.779 degrees. All right, so R of D relative to B is just equal to, I'm going to go BF in the negative I hat direction. So BF minus I hat, right? Because I'm going like that. And then I'm going to go DF in the positive J hat direction. Right, BF is just equal to 0.05 sine 60. That's in the negative I hat. Plus DF is just equal to 0.15 times cosine of 16.779 J hat. Right, so this ends up being, what I got was minus 0.0433 I hat plus 0.1436 J hat. This is in MEE test. All right, that's it. And then we can just go to Mathematica to solve the problem. So let's do that real quick. By the way, before doing that, any problems with the concepts, any questions? All right, so Mathematica. %200%. All right, so let's get our position vectors out of the way. So R of B relative to A is equal to 0.0433. J hat is 0.025. K hat is 0. R of D relative to B is equal to minus 0.0433 and 0.1436 the J hat times 0. Oops, wrong curly bracket. There we go. All right. Next, let's set up all of our knowns and unknowns. So we know that omega AB is equal to 0, minus 94.24, like that. All right, next is I have AD. I'm using capital A. This is weird. The only reason I'm using capital. Oh man. All right. This is acceleration. How do I write it as acceleration? Let's write it like that. Acceleration D. All right. Maybe that's better. All right. That's gonna be T. It's gonna be 0. AD 0, like that. All right. Then we have alpha dB. That we're saying is 0, 0, all right, writing assistant, palettes, writing assistant, alpha, beta, gamma, alpha. And then we're told omega dB is equal to 0, 0, omega, just there. That's B, so that's an unknown. Right, what else do I have as my unknown? So I've got that unknown, that unknown, that unknown. Then I've got AB as my unknown as well, right? So I can write acceleration of B is equal to, let's say, A X and A Y. It's planar, right? So it's only going to be in the ij direction. Then I've got my, where else? What are the unknowns? I've got velocity of point D is equal to 0, comma VD, comma 0. Then I've got omega dB, which is already defined. Then I've got VB, which is equal to VBX and VB, whoops, VBY. Right, I think I have everything. All right, so let's solve. So now we're going to solve for first expression, which is acceleration of D equal to the acceleration of B plus the cross product of alpha dB crossed with R of D relative to B plus cross product of omega dB. Remember, so here's the, basically, this part what I'm doing right now is the new thing we've done. When you're doing a triple product in Mathematica, this is what you got to do. Go from left to right, right? So you're going from omega dB crossed with the cross product of omega dB crossed with that. So you got to say D relative to B. Like that. If you just straight away write cross of omega dB RdB, cannot work. Mathematica only does cross products of two entities at a time. All right. Okay. Next expression is AB. So I have acceleration of B, which is equal to my cross product of like that. But I have omega AB, and I have R of B relative to A. Then we've got VD is equal to VB plus the cross product of omega dB crossed with R of B relative to B. And then I have the final expression, which is VB is equal to the cross product of omega AB crossed with R of B relative to A. Right, that's the expression. And now my unknown is AD. Alpha dB. Omega dB. These two accelerations. D. B. 1, 2, 3, 4, 5, 6, 7, 8. All right. Hail Mary. Fuck out. There you go. Results look good. All right. So make sure you have your requisite units in there. And that's that. Problem solved. All right. Stuff. Any questions, guys? The main takeaway point from Mathematica is that this is how you do the triple product, right? You have to do cross of whatever it is, then cross of the other thing, right? You're going from left to right. All right. So I'm going to move on to the last topic in rigid body kinematics. But before I do that, I've redone this problem using just geometry. Now, this might be a handy tool for you guys if you ever find yourself in a pinch where you don't have enough expressions for enough unknowns. In dynamics, you can potentially use geometry to your advantage to do that. So that solution will be posted as a video for you onto Google Drive. All right, so make sure you look at that. That might be a helpful tool for you to use. If you end up with, you've done everything, you have all your expressions and you double check to make sure you have done that correctly, and you're missing some equations, you might be able to get them from looking at the geometry of the problem. All right, as Mr. Stroud very, very keenly told us today. That's a good suggestion.
Yeah. So the question asked for the acceleration of the piston. What do we get? What did you get for that?
Right here. So it's going to be equal to minus 148,242.
Oh, I see. Okay.
Yeah. Right, you've set it up as your vectors here. So you just have to put them back as vectors and make sure you put the right units in there. All right. Awesome. All right. All right. So with that, say